tried clicking a tiny button on a messy app, missed by just a pixel, and got nothing? Turns out computers feel that pain too. Most AI models that control GUIs still use a clunky hit-or-miss reward system. Click inside the box, you win. Click just outside, too bad. But this new paper flips that logic. Instead of treating every click as black or white, it introduces a smarter reward, Gaussian feedback. The closer the model clicks to the center of a button, the higher the score. And if it's slightly off, it still gets partial credit. Even better, it adjusts the reward shape based on the size of the button. Big buttons, wider tolerance, tiny icons, sharper precision. Welcome to GUI-G 2, where clicking isn't pass or fail, but a smooth dance of probability. Let's dive in.
All right, let's jump right in, starting with Figure 1. On the left, you'll see a performance comparison of different models on the ScreenSpot-Pro benchmark. It's essentially a leaderboard, showcasing how GUI-G squared takes the lead, especially over UI-TAR's 72B. This highlights the model's impressive performance. Now shift your gaze to the right side, where there's a histogram of human click patterns from the AI2 Thor dataset. Imagine it as a map of natural human clicking behavior, forming a Gaussian distribution. This supports using Gaussian distributions for modeling GUI interactions. It's like the model perfectly aligns with how people naturally click. Moving on to the abstract, it sets the stage for GUI grounding, which is about mapping language instructions to specific screen spots. Traditional methods are a bit hit or miss, but this paper argues that's too simplistic. They've introduced GUI-G squared, which uses Gaussian distributions to make interactions more realistic. Picture two main techniques: point rewards for precise locations, and coverage rewards for aligning predictions. There's also an adaptive variance mechanism for handling different element sizes, shifting from binary to continuous optimization. This results in richer feedback, better model guidance, and superior performance, especially on tough benchmarks like ScreenSpot-Pro. It's like moving from black and white TV to color, offering more depth and detail. The research shows strong robustness and generalization, setting a new standard for GUI interactions. Now look at Figure 2 here. It illustrates different strategies for rewarding models on GUI tasks. Starting with GUI-R1, it gives a reward of 1 if a GUI element is identified correctly, and 0 if not. It's a straightforward yes or no situation. Then we have INFGUI-R1, which adds nuance with a fixed threshold of intersection over union, checking the overlap between predicted and actual elements. Now SEGUI introduces some math, calculating rewards based on intersection over union differences, offering a more graded approach. Finally, there's the Gaussian method, which uses smooth Gaussian distributions for continuous feedback. It aligns with natural clicking patterns, offering more fluid guidance than binary and threshold-based models. Moving to the introduction, it sets the scene around autonomous GUI agents, linking natural language commands to precise screen actions. Most systems reward models with a simple 1 or 0, which can be too simplistic. This paper argues human behavior, seen in datasets like AI2 Thor, naturally follows Gaussian distributions, with clicks near target centers. The innovation here? Introducing GUI-G squared, shifting from binary rewards to continuous distributions. By using Gaussian distributions, it captures spatial information and learning signals, with point-based rewards for precise localization and coverage-based rewards for spatial overlap. An adaptive variance mechanism handles different element sizes, improving interaction modeling and efficiency, validated by strong benchmark performance like ScreenSpot-Pro. Let's focus on what makes GUI-G squared special. The authors highlight 3 key contributions. First, they introduce a novel approach that views GUI interactions as continuous spatial processes, shifting away from the traditional binary reward system. Second, a dual-component reward system is proposed. It combines Gaussian point rewards for precision with coverage rewards for assessing regions, enhanced by adaptive variance mechanisms. This ensures the system remains flexible and accurate. The third contribution? Check out those experimental results. GUI-G squared achieves significant improvements over existing methods, with accuracy hitting 92% on ScreenSpot, 93.3% on ScreenSpot version 2, and 47.5% on ScreenSpot-Pro. This shows not just superior precision, but also robustness and adaptability in varied scenarios. In the related work section, they discuss GUI agents, which interact with user interfaces using natural language. These agents fall into two main paradigms: expert design-driven workflows using large language models, and data-driven training with large datasets. Both have strengths and limitations, especially with new or unseen scenarios. This sets the stage for understanding why GUI-G squared's approach is timely and impactful. Now let's explore Figure 3. This visual breaks down how the GUI-G squared framework works. Imagine you've got a task and a screenshot. The policy model, acting as the GUI agent, generates multiple predictions. These predictions are then evaluated using a dual reward mechanism. First, there's the Gaussian point reward for precise localization, like a precise pointer showing where to click. The second part is the Gaussian coverage reward, measuring how well the predicted area overlaps with the target. It's about ensuring accuracy and covering the right spots. This dual approach provides dense learning signals, guiding the model to optimize efficiently. Next, the reinforcement fine-tuning section talks about applying rule-based reinforcement learning across domains, like video understanding and GUI tasks. Previous methods treated GUI elements as discrete points needing perfect targeting. Practical? Not always. GUI-G squared introduces a continuous reward mechanism for richer feedback, crucial for effective model learning, especially in early training. Finally, the methods section reiterates GUI-G squared's introduction, focusing on three innovations: Gaussian point rewards for localization, Gaussian coverage rewards for spatial overlap, and an adaptive variance mechanism for different element sizes. This setup addresses limitations of previous binary reward systems, providing continuous signals that guide learning effectively. Let's dive into the technicalities, starting with problem formulation for GUI grounding. It's about mapping language instructions to specific on-screen coordinates. Picture having a screenshot and a task, with the model predicting a bounding box to localize the target element precisely. The goal? Ensure the predicted center falls within the actual target area. Now onto Gaussian reward modeling, where GUI elements are seen as 2D Gaussian distributions, replacing rigid box boundaries with smooth probability distributions. This naturally captures spatial uncertainty, modeling GUI element positions in 2D space using means and variances. The point reward evaluates localization, checking how closely the predicted center matches the target's Gaussian center. Perfect alignment? Maximum reward? Divergence? Reward decreases smoothly, like a heat map showing accuracy points. Then, there's the coverage reward. While point rewards focus on alignment, coverage rewards assess predicted area overlap with the target area, using the Bhattacharya coefficient to measure distribution similarity. Together, these rewards provide comprehensive feedback, guiding models toward optimal interaction strategies, smoothly integrating predictions with reality. Let's explore the adaptive variance mechanism. GUI elements vary in size, from tiny icons to full-screen panels. To handle this, the model uses an adaptive mechanism that scales variance with element dimensions, ensuring the Gaussian distribution spread is proportional to the element size. This respects natural user interaction with different sized elements, making the model's behavior intuitive and realistic. Now, onto reinforcement learning with GUI-G squared. A model combines precise localization and spatial coverage strengths into a single reward system, integrating point and coverage rewards. This reflects user behavior, aiming for centers but acting within boundaries. It uses group relative policy optimization to stabilize learning by normalizing rewards and balancing contributions, maintaining smooth gradients even when predictions are far from targets, providing clear model improvement guidance. In the experiment section, GUI-G squared is implemented with specific frameworks and GPUs, using large datasets for robust evaluation. This tests model effectiveness in real-world scenarios, highlighting adaptability and precision. Let's break down the performance data. Check out Table 1, comparing various models on ScreenSpot version 1 and ScreenSpot version 2 benchmarks. These test how well models perform GUI grounding across platforms like mobile, desktop, and web. The table splits into proprietary models, open source models, and GUI-specific models using supervised fine-tuning or reinforcement learning. Proprietary models like GPT-4o and Claude Computer Use show varying performance, with lower scores compared to some open source models. Interestingly, GUI-specific models, especially supervised fine-tuning ones, perform better. Models like CogAgent 18b and August v7b show strong results, with August v7b hitting high accuracy in mobile and desktop settings. Now look at Table 2. It shows how different reward systems perform on ScreenSpot version 2. It contrasts sparse reward methods, like point and IOU, with the dense reward method used by GUI-G squared 7b. Here, the dense reward shines, consistently outperforming sparse methods across all device types, highlighting the benefits of dense rewards for accurate and robust performance. Look at Figure 4, comparing reward systems during training. On the left, sparse rewards like point and IOU show fluctuating patterns, indicating instability. In contrast, Gaussian rewards show steady, smooth convergence. On the right, the distance to target centers over time tells the same story. Gaussian rewards consistently reduce this distance, while sparse rewards show erratic changes. Now, onto the main results. GUI-G squared 7b is evaluated against other methods across 3 benchmarks: ScreenSpot, ScreenSpot version 2, and ScreenSpot-Pro. The results? Impressive! GUI-G squared 7b outperforms existing reinforcement learning approaches. On ScreenSpot-Pro, it surpasses UiTAR's 72b by a significant margin, even with fewer parameters. This highlights the efficiency of continuous Gaussian rewards for optimizing performance. The reward design analysis discusses differences between binary and continuous rewards. Binary rewards often fail to provide consistent guidance, leading to unstable training dynamics. In contrast, Gaussian rewards offer a more reliable path to convergence, capturing precise localization and spatial extent. This approach aligns with natural interaction patterns, offering a robust foundation for GUI grounding. Let's dive into how models perform across application categories. Look at Table 3, showing model performance in tasks like CAD, development, creative, and more, both in text and icon contexts. It includes proprietary models, open source options, and specialized GUI-specific models. Notably, GUI-G squared 7b stands out, achieving top scores in several categories, with an average score of 47.5. Impressive, especially in creative and scientific tasks. These findings emphasize how sparse rewards create unstable training dynamics due to restrictive thresholds. In contrast, GUI-G squared demonstrates smooth, monotonic convergence, steadily improving without erratic behavior. The key? Continuous Gaussian rewards offer informative gradients at every spatial position, allowing effective model learning from any starting point. The discussion touches on reward boundaries, considering whether rewards should apply only within target boundaries or across the interface. Insights favor continuous Gaussian rewards for transcending limitations, offering a seamless learning experience. Let's get into how tweaking parameters impacts performance. Figure 5 shows a hyperparameter sensitivity analysis for the adaptive scaling factor, revealing performance peaks at a particular value. It's like finding the sweet spot for tuning a guitar, ensuring harmony for the best accuracy. Now look at Figure 6, diving into the ablation of Gaussian components. It's like testing what happens when you remove parts from a machine. Removing either point or coverage components significantly drops performance. Both are crucial for the model to shine, reinforcing why each piece of the puzzle is essential for optimal GUI interaction. F2. Check out Table 4, comparing Gaussian and distance-based dense rewards. GUI-G squared outperforms SEGUI-7b by a notable margin, emphasizing how Gaussian-based mechanisms better capture the continuous nature of GUI tasks. The text elaborates on these findings, explaining how continuous Gaussian rewards improve learning paths. By spreading these rewards across the spatial domain, the model learns from every interaction, creating smooth paths to target elements. This enhances performance by eliminating optimization barriers and aligning with natural human interaction patterns. Finally, let's delve into fine-tuning GUI-G squared's performance by adjusting reward configurations and thought processes. Look at Table 5, exploring the balance between point and coverage rewards. Turns out, giving them equal weight hits the sweet spot, surpassing configurations that favor one over the other. This balance ensures both precise localization and effective spatial coverage. Then there's Table 6, tackling the thinking versus no-thinking debate. Interestingly, the no-thinking approach, skipping explicit reasoning, significantly boosts performance while using fewer computational resources. This suggests GUI tasks benefit more from a direct perceptual process rather than overthinking. The text further explains the adaptive variance mechanism, scaling reward distributions based on element size, ensuring flexibility without losing precision. The analysis reveals that adhering to a balance principle, neither too strict nor too lenient, optimizes GUI grounding. And when it comes to reasoning, stripping back complexity lets the model focus better on visual tasks, emphasizing simplicity's importance in certain contexts. Thanks for joining us today. Happy exploring together.